We'll start off by looking at section 9.1, which is about hypothesis and test procedures. Now, a hypothesis is a claim either about the value of a single parameter or like several parameters or about the form of a probability distribution. So for example, I can say that X follows a binomial distribution or it follows a normal distribution. We can also have that mu is equal to 68, where mu is the average mark of WSP 121's first class test, or that my P is greater than 0.5, where P is the proportion of students who agree homework shouldn't be given. Or we can compare two averages. So say for instance, we have a statement that says children and adults have the same scores on a memory recall task. Then we can formulate a claim in this form. So we can have mu1 is equal to mu2, or that there is no difference between the two averages, where mu1 is the average score of children and mu2 is the average score of adults. Now, a formal definition says that we have a null hypothesis and an alternative hypothesis. So a null hypothesis is usually denoted by H0, and this is a claim that we assume to be true. So for instance, I can say that my null hypothesis is that mu is equal to 68, meaning I'm saying that the average is 68. Then we have alternative hypothesis, which is denoted by HA, and this is the assertion or claim that is contradictory to H0. So for instance, I can have that mu is not equal to 68. Now, how do we accept and reject? We use like test procedures for that. Now, let's say we have theta, which is a parameter of interest. So theta could be like your mu, your p, sigma, or variance. And the null hypothesis is of this form, which is theta is equal to theta 0. Theta 0 is like any real number, so like 68, 50, 100, whatever. Then the alternative hypothesis can be given in the following ways. We can have that theta is not equal to theta 0, or that theta is greater than theta 0, or that it's less than theta 0. Now you need to know that your null hypothesis can be given in like any form. So it could have been theta is less than theta 0, and then you have to form your alternative hypothesis accordingly. Now, what are test procedures? Test procedures are basically rules that help us decide whether we should accept our null hypothesis or reject it. It is specified by the following 2 points. We have a test statistic. This is a function of our sample data on which we make the decision. And then we have a rejection region, which is the set of all the test statistic values for which we will reject H0. So say for instance, my rejection region is X is greater than 6. And the test statistic that I got was 10. So because 10 is greater than 6, I will have to reject my null hypothesis. Okay, now note that in hypothesis testing, we basically have a claim and then we perform calculations and we decide whether we want to accept it or we want to reject it. And so it involves errors. Now we have two main types of errors. We have type 1 error and type 2 error. Now type 1 error consists of rejecting the null hypothesis when it is in fact true. So your null hypothesis was correct, but you rejected it. And type 2 error is your hypothesis, null hypothesis, was actually false, but you did not reject it. Now, what we have is, we have alpha, which denotes type 1 error, and that's the probability that reject the null hypothesis when, in fact, it was true. And we have beta, which is type 2 error, and it is the probability that do not reject the null hypothesis when it was, in fact, false. Now, you can have a look at this table. What's happening is, we have a null hypothesis. It was true, but I rejected it. So that's alpha, and that's like a false decision. That's not like a correct decision. Then we also have the null hypothesis was false, but I did not reject it, and that's beta. But then we also have correct decisions, which is the null hypothesis was false, and I rejected it. So that's 1 minus beta. It's a correct decision. Or that it was true, and I did not reject it, which is also again a correct decision, and the probability is 1 minus alpha. Now we are interested in the false decisions. Okay, let's have a look at an exercise, exercise 9 from your textbook. So we have two different companies, and they have applied to provide cable television service in a region. So we have two different companies, and P denotes the proportion of all the potential subscribers who favor the first company, right? So let's say we have a null hypothesis that my P is equal to 0.5. So 50% favors the first company. And then the alternative is given as P is not equal to 0.5, which is that 50% does not favor. And so basically it could be like, oh, so our null hypothesis is like 50% favors. So null hypothesis actually means that it's not 50%, so it could be like maybe 40% or like 80%. And then our n is 25, and we have been given x, which is a number in the sample who will favor the first company, right? So if 10 out of 25 favors the first company, then x equals to 10. Now the question is, which of the following rejection region is the most appropriate? So we have the first one where our x is less than 7, less than or equal to 7, or it is greater than or equal to 18. We have the second one which says that my x is less than or equal to 8, and the third one which says that my x is greater than or equal to 17. Now when they ask you to find the most appropriate rejection region, what we need to do is that we need to find the rejection region which supports my alternative hypothesis, right? So we know that in order to get 50 from 25, right? So 50%, we can have like 12.5. So 12.5 divided by 50 is like 0.5. So we want to go away from that. So if you have x is less than 8, so that works because you could take 2, and 2 divided by 25 is not close to 0.5 or like 50%. Or you can take 17, which is also correct because you can have 20, and 20 divided by 25 is not close to 0.5. So we are looking for values which are not close to 0.5. So all of the rejection regions are correct, right? But the one which is most appropriate is the first one. And why is that the case? Because it has both the possibilities of our P not being close to 0.5. So for all values where like x is less than or equal to 7, your P will be not close to 0.5. And for all values where x is greater than or equal to 18, your P will again be further away from 0.5. So rejection 1 takes into account all of the probabilities, like all of the cases actually. And you can also see that our null hypothesis is like not equal to. Not equal to usually comes with like 2 cases. And that's what we have like in rejection 1. So R1 is the most appropriate one. Now, the second question asks for a type 1 error. And we know what a type 1 error is. That's alpha, right? So what we are trying to say, they were actually not asking for a calculation. We are just asked to like write down the type 1 error. So the type 1 error will be judging one of the two companies was favored over the other when in fact there's a 50-50 split in the population. So what does the null hypothesis say? It says that there was a 50-50 split in the population, right? So 50% favored the first company. Now, in your type 1 error, your H0 was actually true. But then what you did was you basically rejected it. And by rejecting it, you are telling us that one of the two companies was favored over the other, when in fact it was not true, because like 50% favored the first company and 50% favored the second company. Right. Alright, so now C asks us to compute the probability of a type 1 error. So the first thing we need to understand is that the test statistic, which was X, so the number of people who favor the first company, is approximately binomial with n equal to 25 and p equal to 0.5. Now if you see, p equal to 0.5 is actually our null hypothesis. So this is what null hypothesis is true translates to. So we have alpha, which is a type 1 error, and by definition it's the probability that I'm going to reject my H0 given that it is true. Now H0 is true, it translates to X follows a binomial with 25 and P 0.5. Then when do we reject the null hypothesis? So if you check like A, we chose our rejection region to be this part. So that is when my X is less than or equal to 7, or it is greater than or equal to 18. So that's the rejection region we chose. Now how do we go from here to here? Let's choose the probability rules. So where do we use the condition? The condition is used in order to find a probability. So the capital F, the cumulative distribution function, will be used for a binomial distribution. So I cannot use a normal distribution, right? So that's taken into account. Now, probability that x is less than or equal to 7, or they all translates to plus. Probability that x is less than or equal to 7 is just this part, which is the cumulative distribution, or f, the capital F of 7, when n is 25 and p is 0.5. And p greater than equal, x greater than or equal to 18 is just 1 minus x is less than 18. So that's why we have a 17 there, because this is a discrete distribution. So if x is greater than or equal to 18, then the opposite will be x is less than 18, which is x is 17, so less than or equal to 17. And these are the probabilities that I got from Excel, and then your final answer will be 0.0432. Now for D, we are asked to compute the probability of a type 2 error. Now for a type 2 error, we can have like different types of probabilities. So there is not like one fixed answer, because it will change for whatever p you are given in the question. So you could have given 0.3 or 0.2. Anyways, beta, so this is the probability that your beta is a type 2 probability, and this is a probability of not rejecting H0 when H0 is actually false. So what does this mean? H0 false, that translates to my p equal to 0.4, because remember we said that p is equal to 0.5. Now we are saying that that's not the case. P is actually equal to 0.4, which makes the null hypothesis to be false. And do not reject the null hypothesis. So what was our rejection region? It was x is less than or equal to 7, or x is greater than or equal to 18. So if this is a rejection region, what's the not rejection region? That is basically x has to be greater than 7, and x has to be greater than 7, and x has to be less than 18. But that's the same as saying that my x is greater than or equal to 8 and less than or equal to 17. Because it's discrete, the moment you get an equal sign here, you have to change your 7 to 8 and 18 to 17. And then I just use the probability rules to go from here to here, then Excel or your tables, and this is your final answer. Cool. Now the last question asks, what's using the selected region, meaning this part, x is less than or equal to 7 or x is greater than or equal to 8, what would you conclude if 6 out of 25 clearly favored company 1? So what if my x is actually 6? So our selected region was actually x is less than or equal to 7 or x is greater than or equal to 18. Now, since I have 6, which is less than or equal to 7, I will have to reject the null hypothesis in favor of the alternative hypothesis. If I had, say, for instance, 24, then I'll also reject the null hypothesis because 24 is greater than 18. But if I had something like 9, then I cannot reject it. So that's it. All right, so now we move on to section 9.2, and this is the test about a population mean. So our parameter of interest will be mu. Now there are 4 steps that you can follow in order to test for hypothesis. The first one is you need to determine what your null and alternative hypotheses are. Then you need to compute the test statistic and find the critical value or the rejection region, and you have to conclude. So for the first case, we have a normal population with a known sigma. So in your question, you will be given that your x or your y follows a normal population, and the value of sigma, so your standard deviation, population standard deviation, is also known. Now, how do you proceed? So the first thing that we're going to do is find a null hypothesis. So say, for instance, you have mu equal to mu 0, and mu 0 will also be given in the question. Then you need to get your test statistic value, and this is the one for case 1. It's a very common one, x bar minus the mean divided by its own standard deviation, so sigma divided by root n. Now, alternative hypothesis could be mu is greater than mu 0, or mu is less than, or mu is not equal to mu 0. Now, alternative hypothesis is really important because in step 3, we are going to find rejection regions, right? Now, rejection regions are based on alternative hypothesis and not the null hypothesis. So for mu greater 0, we have this rejection region, which is your z. So your z is actually your test statistic value, and the Z alpha is the critical value that we get from the tables. So if your Z is greater than or equal to Z alpha, then you are going to reject your null hypothesis. For the second case, if your Z is less than or equal to negative Z alpha, then you are not going to reject it. And for your third case, this is a two-tailed test. If your Z is greater than or equal to Z alpha over 2, or it is less than or equal to minus Z alpha over 2, then you are going to reject your null hypothesis. Take note that for one-tailed test, your alpha, like it's just alpha, so you do not divide it by 2. But for two-tailed, you will have to divide it by 2. Okay, so let's have a look at exercise 25 from the textbook. So we are given a random sample of 10 of the IQ scores for grade 1 learners, and we have been told that the test score is approximately normal with a mean of 100 and a standard deviation of 15 for the entire population, meaning the 15 that we are given is sigma. Now we are interested in seeing whether the population of the first graders at this school is different from the national population, and test this at a 0.05 significance level, meaning alpha is 0.05, to see whether the school mean differs from the national mean. So the first step is find your null hypothesis and your alternative. So your null hypothesis will be mu is equal to 0 versus mu is not equal to 0, right? Because we want to test whether the population is different from the national population. So whether the sample of the school is different from the national one. Now what's the national mean? That's 100. So that's going to be your null hypothesis, and different meaning it is not equal to. So like it's basically it could be greater than or it could be less than. The second thing we do is our test statistic, and we saw that this is what we had. So we had like x bar minus mu divided by sigma and root n. So we just substitute everything. Your x bar is found using this formula. So you sum all of them up and you divide it by 10, or you can also use like calculator for it. Like this, I think like a stat function or something. So your x bar is 116, your mu 0 is 100, your sigma is 15 as given in the question, and your n is 10. And the value that you got is 3.37. So this is your Z. Okay, so now the third step includes finding the rejection region. So we have our alpha, which was given as 0.05. Now we know that this is a two-tailed test, so we need alpha over 2, 0.025. From your tables, you can get this value, which is 1.96. Now we are going to reject if my Z, the one that I found in step 2, is greater than or equal to 1.96, or if it is less than minus 1.96. And clearly 3.37 is greater than or equal to 1.96. So we actually reject our agent 0, and then you should like explain it. So we are saying that the mean IQ for all first graders at this school is significantly different than the national average of 100. Because we said that, okay, the school mean and the national mean is the same, but we ended up rejecting it, meaning it is significantly different. Okay, now let's have a look at the second case, which is a large sample test. So in such questions, you will be given a very large sample test, such that like your n will be greater than 30, so you can use a CLT. The question will not tell you that the data is approximately normal, but from CLT, we can assume that it is approximately normal. Now, once the assumption has been checked, you replace your sigma, the population standard deviation, by S, the sample standard deviation, and you proceed as in case 1. Now, let's have a look at example 9.8 from your textbook. So we are given a sample of bills for meals from a restaurant, and the question asks, does it appear that the population mean tip percentage for this restaurant exceeds the standard 15%? So your mean will be mu, and this is your mu 0, and exceeds meaning greater. Another thing is that this was the data I got from like the textbook, and your n, the sample size, was actually 70. So I forgot to like mention that. Sorry. Now the first thing you do is formulate your hypothesis. So your null hypothesis will be mu is equal to 15 versus your alternative, which is mu is greater than 15. Now why do we have greater than? Because the question specifically asks for exceeding what. The second step is go ahead and have your test statistic. So you check your n is equal to 70, which means it is greater than 30. You can use CLT. Now your Z is equal to x bar minus 15 because that's mu0 from the question, and you have your S, which is 5.937 divided by square root of 70. Now your X bar and your S were found from the data. You need to note that for S, this is a formula that we use. So this is the variance formula, but then you square root it in order to get the S. Now don't worry, in a test or exam, they won't really give you like 70 observations, but these are the formulas that you need to note. And the final answer is 4.21. Let's have a look at exercise 27. So we have like bagels, and on its label it was written that they all like weigh 113 grams. And we have a random sample of only 6 observations, and this is what we were given. Now you need to understand that we were not told that the bagels follow a normal distribution, so we cannot use case 1. 6 is also like less than 30, so we cannot use CLT, hence we cannot use case 2. So we have to use the last one, which has a t statistic. Now the question is, based on this sample, is there any reason to doubt that the population mean is at least 113 grams? Now we know what at least means. It means greater than or equal to. And because we have used the word like doubt, what basically it's telling us is that my null hypothesis was mu is greater than or equal to 113. Is there any reason to doubt that? Meaning, is it possible that my mu is less than 113? And that will be my null hypothesis. Now the second step, you get your t statistic. So again, it's going to be x bar. So from your sample, minus 113 s using the formula I just gave like in the one of the slides, and divided by n, which is 6. And the answer you get is negative 0.02. So it's possible to get a negative test statistic too. Now the third step is you go ahead and find your critical value. So in this case, because it's a one-sided, we don't divide alpha by 2 and assume your alpha was 0.05. Then your n minus 1, so your degrees of freedom is 5, and from the tables we get 2.015. Now we again have to look at the null hypothesis. So because it's mu less than, we will reject if my t is less than or equal to negative of the critical value I just found. So if my t is less than or equal to minus 2.015, I will have to reject. And because t is greater than, because remember we're dealing with like negatives, so negative 0.02 is greater than negative 2.015, we cannot reject another hypothesis. Hence, we are not sure that like there is no like significant evidence that a population mean is not at least 113. So we cannot like just reject hypothesis. And yeah, that's it. Thanks.